Okay, okay, perfecto. So thank you very much, everyone, for being here today. My name is Manfred Gonzalez Hernandez. I am from Costa Rica, and I am right now a PhD student at Technical University of Eindhoven in the Netherlands. Today, I'm gonna show you guys a bit of conditional flow matching. This is a topic that I have been working on for a while. Basically, this is a new, generative paradigm for images, audio. Also, you can see some applications in biology, some clinical experiments as well with images, clinical data, and several modalities where flow matching have shown a really good performance, in several applications. So I think you guys have seen, like, for example, some real life applications where you have like some applications where you can just write a prompt and you can create a video like movie gen from Meta, also like text to image from Stable Diffusion 3. Um, in these two applications, you basically have directly flow matching in their algorithms, right? Stable Diffusion, they use a bit of the diffusion techniques, but also they use in their core application flow matching, as well as movie gen. But you have also protein generation and robot action model applications where basically you try to generate and also forecast some scenarios based on a prompt. So if you guys are asking like what is flow matching, right? Like basically you have a method to train a flow generative model in which when you train, right, you try to regress the velocity, but when you sample, you try to follow the velocity. So in a nutshell, when you're training a flow matching model, you are basically trying to go from one distribution, simple distribution, to a more complex distribution. When I talk about distributions, let's say you have a distribution of images, right, of dogs, for example, uh, and you want to generate synthetic images of those dogs. Well, basically, you can generate images if you follow the training scheme and the sampling scheme of flow matching. You do this by basically trying to regress the velocity that will draw or will create a straight path from the simple distribution to your target distribution. Normally, the simple distribution is a Gaussian. We'll see this in further slides. So like I mentioned before, let's say you have this space of images, right? And in one part, you have this simple distribution, which is Gaussian noise, which is x0. And you sample an image from this simple distribution. And basically, you want a function phi that will bring x0 to x1. Basically, in flow matching, this phi function is going to be the one that will regress the velocity to sample this velocity in testing time to generate new images. We have in the state of the art, we have some examples where you can see approaches of, like, for example, diffusion models. That diffusion models, they are basically stochastic because they try to learn the reverse process of denoising images, right? And they do this by basically putting the Gaussian noise into the image, right, and trying to denoise it. But in each denoising step, they add a little bit of noise back into the image. And that's why you have a noisy path from your simple distribution to your complex distribution. But this is the figure in the center. So you can see that it's a bit curly because you are adding stochasticity into the path. And basically you will have a random trajectory to the target distribution. You have jump models, And also you have one-shot generative models like GANs, generative adversarial networks, right? But some years ago, flow models have been, like shown that they have quite good performance in generating data, and they do like they try to do like a marginal probability path to go from this simple distribution to the complex one. But if you heard about normalizing flows, for example, they tend to be very complex to be trained. Normally, they have to simulate each of these steps of the intermediate steps of this trajectory until you reach a more complex distribution. But flow matching came to solve this problem in a really simple way and also straightforward to be able to train um, your algorithms and generate in a way easier way new data. So what are we doing here? Well, we basically use differential equations. In diffusion models, you have this stochastic differential equation, which I told you before that it's been modeled by trying to learn a denoising network. And basically you try to add back in each of the intermediate steps some noise into the image to not lose too much control over their generation. But in flow matching, we are using an ordinary differential equation. How does this look? Well, basically, you define a smooth time varying vector field that it's U. Basically, this vector field is going to be the one, right, that will help you to guide your distribution from one distribution to another one. But basically, with this vector field, you define the ordinary differential equation, and you have two initial conditions. First, that the result of this differential equation at time step 0 is going to be the same as the data that you already have in your data set, let's say a dog, right? And the other one, the other initial condition is that you need to keep the continuity equation in your math. Basically, which it says is that the trajectory is continuous and it's also differentiable when you go from one distribution to another one. And this function phi is basically the trajectory, or the result of this ordinary differential equation that will transport in several time steps your your data from the simple distribution to a more complex distribution. And this basically says that PT, right, could be like a push forward measure that will, like I said before, push forward your data from the complex distribution to from the simple distribution to a more complex distribution. So the idea of flow matching is that you need to regress the vector field, this vector field that will push or will guide, your generation of the data. And basically, if you have V theta, that is going to be your network, that is that V theta will try to predict this velocity, right? But you need this theoretical vector field that will serve as a ground truth, right? So you need the predicted velocity, but you need the ground truth velocity. And these two, like the ground truth velocity and also the data distribution PT, right, is unknown. You don't have it, right? So basically you have to do some tweaks here to be able to make this to work. Um, the solution that they found was, okay, in terms of math, what we can do is that we can condition these marginal probability paths, right, with known distributions that we know. And basically they said, okay, we can marginalize our probability path, right, based on a conditional variable that it's Q of set, that basically you define the marginalization of PT of X given set by a normal distribution. What is this trying to tell us is that if you couple your data with data from a normal distribution, right, you will be able to have, or you will be able to control or to know this conditional probability path. And you will be able to then train this model by doing some tweaking into the vector field. So once you define this probability, this conditioning using a normal distribution, then you update the vector field and you say, okay, now my vector field, right, can be conditioned to that conditioning variable that it's this set. And after some math and some theorems that they showed in the paper, they came up that the simplification of this math is basically the distance from x1 to x0. And this is the theoretical velocity that you need to regress in your loss function. This is very important because when you were using normalizing flows, when you were using, for example, diffusion models, you needed way more intermediate steps. For diffusion, for example, you needed to define, for example, um, in the initial steps of diffusion, you had to learn first the covariance matrix and then the mean. And they used two separate networks. Then they simplified with other algorithms, like for example the DPMs, in which they said, no, the covariance we will solve the covariance with some defined values, but for the mean of the standard distribution, we will we will learn it with the network. And then after learning these, components, they had to frame more complex math to be able to come, with a feasible solution for diffusion models. For normalizing flows, they had to define several invertible functions that they had to um, model each of these invertible functions to be able to understand how to generate this synthetic data. In this case, for you to train a velocity, right? After all the math they did, they found out that it was super simple by just computing the distance from x0, that basically x0 is like this Gaussian image, which is like full of noise, and x1, that basically is your target image, right? So how does it look in code? Basically, this is a screenshot of their tutorial in NeurIPS, where they have x1. That x1 is just a 2D vector of, they call it moons, but basically it's like a group of points in a plane, and they wanted to regress these points in this plane, right? So they have x1 that it's, let's say, their desired or their target image. X0 is their starting point, right? Which is a Gaussian image. And then they wanted to train at a certain time step, and to be able to create an image at a certain time step is just a linear interpolation between x1 and x0, right? And once they had this image at a certain time step, they take it, right? And they want to regress the flow or the velocity uh, of that basically intermediate image. Once you regress the velocity, you can see here in loss dash fn flow, this xt is the intermediate image that they are trying to regress the velocity, and the theoretical or the ground truth here, right, is just the distance between x1 and x0, right? The target image and the Gaussian noise. They plug that into the mean square error, and that's how they optimize this network to be able to learn at any point of this trajectory the velocity. And once you are sampling to create new images, you basically use the same network to use the velocity to follow the velocity towards the desired data that you want to achieve. So which algorithms or which applications can we see that um, have been using flow matching in the state of the art. This is one of the examples in biology and life science research. You can see that the number of papers for the late years, for example, NeurIPS, ICLR, and ICML is increasing a lot by using flow matching in their applications. One of the applications I noticed in the state of the art they have been using the most is the 3D molecule generation. They basically try to, based on some guidance, on some prior knowledge of some molecules, they will be able to generate uh, new molecules out of the ones that they already had. And also another example is for weather forecasting. So as you can see, you have the ground truth in the top row, and you have several algorithms. You have classical units, then you have like transformer-based models, and some other state-of-the-art algorithms for weather forecasting. But for example, the algorithm using flow matching, that it's Flowcast, was like the one that was shown in this paper that basically performed the best to predict correctly the weather in 10 minutes, 20 minutes, 30 minutes, 40 minutes, 50 minutes, and 60 minutes. This paper was shown in ICLR in May, actually, in this month in Brazil. And right now, this is state of the art in weather forecasting. So you can see that flow matching can be used for lots of application, time series, image generation, molecule generation. It has tons of applications. I wanted to make this presentation as short as possible because I'm open for any questions. Thank you very much, guys, for your attention, and let me know if you guys are interested. Thank you.
Muy chido, muy interesante. Ah, bueno, listo. Ahora sí creo que ya no me voy. No, la verdad sí me parece bastante interesante ver primeramente como la cantidad de implementaciones que se están usando con el algoritmo en los últimos años y también ver como el tipo de conferencias que ha podido llegar. Este, entonces me parece algo muy interesante saber como que existe, que se está usando y también una duda que me puede llegar a generar. Creo que no lo vimos, pero más o menos cuáles podrían llegar a ser como los porcentajes en métricas que logran alcanzar. Me imagino
Claro.
que para ser un método que está en auge debería ser bastante bueno, pero no sé si tal vez tendrás un dato, tal vez de alguno de los
Claro.
experimentos que estén.
Mira, em, para medir, digamos, estos modelos generativos en imágenes, por ejemplo, que es el área en el que yo me desenvuelvo, normalmente se usa una métrica que se llama Fit Score, que básicamente es como Freshet Inception Distance, que básicamente mide como qué tan buena calidad y perceptual también tienen tus imágenes. Normalmente, Diffusion andaba por los órdenes de 4 punto algo en Sci-Far, que es un dataset bastante conocido, pero Flow Matching ya llegó al 3.6, o sea, entre más bajito mejor, y Flow Matching ya como que superó en algunos datasets, incluyendo a Diffusion Models. Entonces, creo que por ahí
Va bien,
va muy, muy bien. Y lo que más impresiona del caso y a experiencia personal es la simpleza del código. O sea, es demasiado fácil utilizar flow matching. Yo les enseñé digamos que el tipo de flow matching más sencillo, que es el independiente, pero hay uno que se llama Optimal Transport, que
ok.
básicamente asegura que tus trayectorias son completamente rectas Entonces, te hace una generación muchísimo más eficiente y muchísimo más rápida. Entonces, como ves, se han hecho como updates sobre el mismo para- eh, teorema que va haciendo la generación de imágenes más fácil y más factible, ¿verdad? También para darte un
Ujú.
ejemplo, yo ahorita, bueno, en mi doctorado estoy trabajando con unas imágenes son como unos mapas de poder que se utilizan en algunos chips como CPUs y GPUs, que te dice
Ujú.
básicamente en qué lugar del CPU se está activando más la electricidad o que está consumiendo más poder. Y queríamos predecir la temperatura asociada a ese consumo de poder. Y
Ok,
básicamente entrenamos un algoritmo de flow matching y nos dio un SSIM de 0,87. Luego agarré un Variational Autoencoder, que es como Classical Machine Learning Algorithms, lo entrené con 3000 y resto de imágenes, mientras que Flow Matching solo con 37 y,
ok.
s- y el Variational Autoencoder no pasó a más de 0,77. Entonces, con menos imágenes y muchísimo más fácil, Flow Matching llegó a superar un Variational Autoencoder, por ejemplo, con muchísimas más imágenes, ¿verdad? Em, entonces ha sido muy, muy, muy interesante ahondar más en este tema. Y también otra ventaja, Samir, perdona que me extienda tanto, pero otra ventaja que tiene esto es que en esta imagen, como ustedes ven aquí al lado derecho, si yo hago un sampling de esta distribución y agarro n cantidad de x ceros, que puede ser cualquiera, o sea, puede caer en cualquier lugar de esta distribución, para generar la imagen x1, yo voy a tener una medición de la incertidumbre de qué tan bueno es mi algoritmo, porque con solo cambiando eh, imágenes random me va a dar
Ujú.
inferencias de distinta calidad y ya yo podría medir mi algoritmo qué tanta incertidumbre tiene, por ejemplo, en los datos o en el modelo. Entonces, da para mucho, es muy fácil de usar y la idea de esta presentación era que lo conocieran muy por encimita pero para que se puedan ir familiarizando con él y lo puedan ir utilizando para que vean lo sencillo y lo gran útil que es.
Y computacionalmente hablando, me imagino que no es tan pesado como otros modelos.
Dependiendo del modelo, digamos, del modelo que utilices para regresar la velocidad.
Ujú.
Pero, por ejemplo, yo ahorita estoy usando un modelo Unit que es pequeñito. Em, bueno, le quité algunas capillas ahí para no hacerlo muy grande. Y básicamente logré entrenar este algoritmo que te dije de predicción de temperatura con mi computadora, con una GPU de 8 gigas, digamos. Y entrenó, ¿qué te digo? Como en menos de una hora, 10 épocas. Entonces, al ser mucho más eficiente que Diffusion, te es más factible entrenar modelos de generación. Cambio Diffusion, jamás, o sea, yo he entrenado modelos de Diffusion y nunca lo he podido entrenar en mi computadora, eso ya hay que mandarlo a un cluster. Entonces sí, mucho mejor.
Ok, ok. Dino, muy interesante. Yo creo que es algo nuevo que aprendimos y bueno, por lo menos a mí sí creo que es algo que voy a ver más a fondo. No sé si alguien más tuviera como alguna pregunta o comentario.
Espero no haberlos aburrido. La quise hacer
No,
cortita
no,
por lo mismo.
más bien yo creo que estuvo muy interesante. De hecho, lo que te iba a decir era si me pudieras pasar un par de papers para poder ver la idea tal vez más desarrollada y
Claro,
esos papers los compartiría con los asistentes.
de fijo, les puedo pasar los papers, esto fue un tutorial de NeurIPS, entonces puedo pasarles el tutorial de NeurIPS y les voy a pasar también el GitHub oficial porque hay unos ejemplos que ustedes pueden descargarlos y correrlos nada más. Entonces ahí se los voy a pasar.
Ok, listo. Yo creo que estuvo muy interesante, la verdad. Entonces, Dino, agradecerte, Manfred, por tu tiempo y por enseñarnos esta nueva opción. La verdad que está muy, muy interesante.
Con muchísimo gusto, Samir. Hay cualquier duda o consulta, pueden contactarme y Siempre es un placer colaborar. Pura vida.
Listo, nos vemos.
Nos vemos. Hasta luego.
Chao, chao.